Hello, and welcome to this session. LO5. Understand the fundamentals of assembly language and how it relates to higher-level programming languages. In this session, we will explore a central question: how does software communicate with hardware? Assembly language serves as the critical bridge between human-readable code and machine instructions. This video introduces the fundamentals of assembly language and explains its relationship with higher-level programming languages, helping you understand how code is translated and executed at the hardware level. Assembly language is a low-level programming language using mnemonic codes. It is closely tied to machine code, specific to processor architectures like x86 or ARM. Assembly provides direct hardware access, making it essential for understanding low-level operations. It is less abstract than high-level languages, allowing detailed control over implementation. This chapter explores the core components of assembly language. Correct. Assembly language consists of opcodes, operands, registers, labels, and directives. Opcodes define operations like MOV or ADD, while operands specify data or addresses. Registers are small storage locations within the CPU. Labels identify memory locations or jump points, and directives guide the assembler. Understanding these components is key to mastering assembly programming. High-level languages like C and Python focus on logic and algorithms, abstracting hardware details. Assembly language is specific to processor architecture, offering direct CPU and memory access. The compilation flow involves translating high-level code into machine code through assembly. This section compares the abstraction levels and control offered by both language types. Understanding these differences is crucial for system-level programming. Learning assembly language is vital for performance tuning, system-level programming, and security analysis. It allows optimization of critical code sections for speed and efficiency. Assembly is essential for OS development and understanding code translation. However, it is not portable and can be error-prone. The benefits and limitations are important considerations for programmers. Assembly provides direct control over hardware and system resources. It allows manipulation of CPU registers and precise memory management. This is crucial for writing device drivers and performance-critical applications. Operating system components often rely on assembly for speed and precision. Understanding assembly is essential for hardware interaction and optimization. Assembly offers full hardware control, but is complex and CPU-specific. High-level languages are abstract, portable, and easier to maintain. They provide built-in error handling and debugging support. Assembly is faster if optimized, but harder to manage manually. Understanding these trade-offs helps in choosing the right language for specific tasks. Let's look at a simple x86 assembly program. It writes "Hello World" to the console using Linux system calls. The program demonstrates the use of registers, system calls, and interrupts. Understanding such examples highlights the direct interaction with hardware. This knowledge is foundational for low-level programming. Assembly languages are architecture-specific, like x86, ARM, IPS, and RISC-V. x86 is complex, used in desktops, while ARM is power-efficient for mobile devices. IPS and RISC-V emphasize simplicity and are popular in education. The choice depends on the architecture and application needs. Understanding these differences is crucial for effective programming. Different architectures have unique features and use cases. x86 is known for its rich instruction set and complexity. ARM focuses on power efficiency and simplicity. MIPS and RISC-V are valued for their educational and research applications. Evaluating these factors helps in selecting the appropriate assembly language. Higher-level languages abstract away hardware complexities using English-like syntax. They are translated into machine code through compilers or interpreters. This abstraction improves readability and maintainability. It allows programs to run on multiple platforms with minimal changes. Understanding this abstraction is key to modern software development. Abstraction enhances readability and maintainability by simplifying code. It supports portability across different hardware platforms. Faster development is achieved through built-in functions and libraries. Error handling and debugging are more accessible in high-level environments. These benefits make high-level languages essential for efficient programming. Abstraction involves translation tools and runtime environments. High-level code is converted into intermediate and machine code. This process introduces some overhead but is mitigated by modern optimizations. The abstraction layers balance performance with development efficiency. Understanding this process is crucial for effective software engineering. ARM assembly is widely used in embedded systems. It follows a RISC architecture with simple instructions. Basic routines involve understanding registers and instruction formats. Implementing arithmetic and control flow operations is fundamental. This knowledge is essential for developing efficient embedded applications. An ARM program consists of sections for data and instructions. The entry point is defined globally and code execution starts there. System calls are made using software interrupts. Understanding the program structure is key for effective ARM programming. This section provides a foundational overview for beginners. Let's explore adding two numbers using ARM assembly. The program loads values into registers and performs addition. This demonstrates the use of basic arithmetic instructions. Understanding such examples is crucial for mastering ARM assembly. Practical exercises reinforce the learning of assembly concepts. This ARM program sums numbers from 1 to 5 using a loop. It demonstrates control flow with branching instructions. The program highlights the use of comparison and conditional branching. Understanding loops is essential for developing complex routines. This example reinforces the concepts of iteration in assembly. Key ARM instructions include MOV, ADD, SUB, and CMP. Branch instructions like B, BLT, and BEQ control program flow. S2I is used for making system calls. Mastering these instructions is crucial for effective ARM programming. This section provides a concise reference for common operations. Use ARM emulators or devices like Raspberry Pi for practice. Focus on writing small routines to master loops and conditionals. Experiment with arithmetic and control flow operations. Practical exercises enhance understanding of assembly concepts. Consistent practice is key to becoming proficient in ARM assembly. Explore resources like ebooks and journals for deeper insights. Online platforms offer interactive lessons on assembly and computing. Reference materials provide comprehensive guides on ARM assembly. Continuous learning is essential for mastering low-level programming. This section highlights valuable resources for further exploration. In conclusion, a solid understanding of assembly language is fundamental to modern computing, providing essential insight into how software interacts with hardware and underpinning the development of more complex programming and system-level operations. We appreciate your attention. Should you have any questions, please contact UKversity via WhatsApp at 07000 484 361,688. Thank you, and we look forward to seeing you in the next session.